Every once in a while, I come across people that manage to get me really excited about a specific topic and are able to convey such a sense of wonder and amazement about it. Today's conversation with Tom Ager is about radar images, how they work and why they're important. If you've ever looked into satellite imagery, radar images might have come across as interesting yet confusing and hard to grasp. While we do talk about the engineering behind these images, this is also a conversation about the wonders of engineering, breaking down and understanding complicated topics and simplifying for others to grasp and maybe even more importantly, get excited about. Tom worked at the National Geospatial Agency for 30 years, was involved in the development of classified radar imagery before leaving the agency and writing a book about synthetic aperture radar, which he often refers to as being written for non-electrical engineers. His book is, in my opinion, one of the most accessible yet thorough resources anyone wanting to learn more about this topic can find. But beyond the engineering and the physics, Tom also has a knack for poetry and writing. This episode is sponsored by Planet. If you work in the satellite image world, you probably already know about Planet. They're one of the biggest providers of high-frequency, high-resolution satellite imagery today, and their open, accessible platform integrates seamlessly with different GIS platforms, making it easier to access their high-cadence, pre-processed data, allowing you to focus on the analytics. Now, historically, getting access to high-cadence, high-resolution satellite imagery has been overly complicated and time-consuming. This is something that gets often discussed on this podcast. Planet has direct integrations for desktop GIS software like QGIS or ArcGIS Pro and continues to develop flexible APIs to build custom imagery pipelines. They also recently acquired Synergize, the company behind Sentinel Hub, giving even more options to get access to Planet imagery. Most of the work we should be doing should be focused on the analysis, not on getting the imagery. To learn more, head over to planet.com/GIS. I'll have a link in the show notes. Thank you again to Planet for sponsoring this episode. I don't know if you know, I actually like starting these the same way every single time. I like asking people how they would describe themselves. You've done a lot. You've worked at the NGA. You've written a book. You do some consulting. So I'm curious, how would you describe yourself?
I've been retired, semi-retired for 10 years, but when I was working, I always thought of myself as a technically skilled program manager. Because I was the face of the SAR program at NGA, some people came to think of me as some brilliant SAR scientist. That's not the case. I do have a technical graduate degree, but it's in geodesy and photogrammetry, not electrical engineering. So I was a technically skilled program manager who knew kind of what to do, how to work with people. I worked with brilliant people. And I would say I always felt like I was throwing a javelin with a flag on it, right? That was my job. That's how we ran the SAR program, which we'll talk a little bit more about that. And the other thing is that I was always a teacher. I have a great interest in understanding the way things work. I've always been curious about physics and science. And so I was able to figure things out, how things worked, and explain it to my coworkers. And so that is the other aspect of how I would describe myself. Program manager, very motivated one, in a renegade, strange science, and a teacher.
I want to make this conversation as approachable as possible. So I'm going to ask you to elaborate on a lot of things. We've started the conversation with quite a few acronyms already, and I'd like to go back and try to define some of those. So we're going to talk about SAR in a minute, but you said you worked at NGA. Can you just tell me what NGA is, what they do, and maybe a little bit more about what you were doing there?
Yeah, so that is the National Geospatial Intelligence Agency. It is the agency within what I like to call the United States military intelligence complex that uses spy imagery to watch things over the world. The agency that builds the spy satellites, that's called the National Reconnaissance Office. So basically it was the NRO building, launching, in our case, optical and radar satellites to observe the Earth. We use them to do things. There were predecessor agencies before NGA, but let's just call them all NGA because it really was the same place, expanding its mission over the years. And I've moved around within that agency and worked a lot with the NRO.
Got it. And just for context, when do you join the NGA?
I started working there in 1983 and left in 2013, 30 years.
Wow. Okay,
Yeah.
1983.
Young guy, a long time ago, 1980.
Let's get into SAR, Synthetic Aperture Radar.
Yeah.
If I'm someone that's heard about this thing, there's satellite images, I'm kind of familiar. I've, maybe seen on Google Maps, you can turn on the satellite layer. Maybe I even know that it's not really satellites, but I have a grasp of what a satellite image. I've seen it on the news. Recently with the invasion of Ukraine, we've seen satellite images. And I've got a grasp that there's this other sort of stuff out there that's these radar images. How would you go about explaining to me what those are? And maybe even before that, why should I even care?
All right. So you should care because we live on planet Ocean. We call it Earth because we're biased land creatures, but 70% of the surface of this planet is water. So there's a lot of water vapor in the air and a lot of clouds. And so if you want to take a picture somewhere over this planet and you need to see what's going on, you cannot use visual wavelengths unless you get lucky because you're going to see clouds about 70% of the time. So we need to use a different part of the electromagnetic spectrum that goes through clouds. And the nearest part outside of visual is the microwave region. So a synthetic aperture radar sensor uses microwaves. And if we're going to just do a very simple explanation of it, I'd like to think of it as a microwave strobe light. We're flying a satellite or an aircraft and sending out microwave pulses and recording the echoes. Right? It's like a strobe light of microwave energy. It's going to go through the clouds, so you're going to get a picture. So it is famous for getting pictures through clouds and through darkness. You don't need sunlight to do it. But the other aspect of it that's crucial is that the pulses we send are coherent. They're like laser beams in which we control the structure of that pulse. We know what it looks like, and we make sure every pulse is the twin of the previous pulse. They all look alike, and that means we can measure phase very precisely, which we'll talk about a little bit later. So it has the ability to go through clouds, image in darkness, and the illumination allows me to measure phase, which we can do remarkable things with. You cannot do with optical sensors. May I say why we call it synthetic aperture?
Sure. Let's do it.
Okay, so if you do that with a physical aperture, like an antenna of 6 meters long, you would get terrible resolution. It's because the wavelengths are much longer than optical wavelengths. Optical wavelengths that we see with our eyes are about a half of a millionth of a micron in length. The wavelengths we use for SAR are measured in centimeters or even in some cases meters. So they're much longer. You can't get the same resolution given a physical aperture. So a brilliant guy in the 1950s figured out how we could make a synthetic aperture by taking lots of pulses as you fly across and building a very large synthetic aperture from the action of a small one. So we call it synthetic aperture radar, and it is equivalent to putting a giant antenna up in space. In some cases, perhaps we'll talk a little bit later about how you get high resolution from this. The size of that synthetic aperture is immense. It's really remarkable. One of the wonderful things about SAR.
Let me go back to the justification of why. And so we start with the clouds. Maybe a naive question, but I'd still want to ask it is, why don't we just fly planes below the clouds? Like, Why do we have to use a satellite in the first place?
All right. So would you like to be in that airplane right now if it's flying over Ukraine? I don't think
Fair
so.
point.
No, I don't think you would. And to get them up all the places you want, it's not viable from aircraft. Certainly, aircraft are very, very useful. And in some applications, you want to see big, wide pictures. SAR is good at tracking ice in water. So if you want to look at climate change impacts to the Antarctic, for example, you want a big picture that you're not going to get from an aircraft. You may, a few hundred kilometers width and length. Can't do that from an airplane, and you just can't have airplanes everywhere. So space imaging, space remote sensing is really important.
Fair enough. I think I always like asking these
That's
questions.
a good question. Sure.
We'll dive into a little bit more of the technical aspects of SAR, but before that, I want to go back in time, all the way back in 1983. You joined NGA, and what can you tell me about some of the work that you did there, and maybe how you got into synthetic aperture radar, what the world of SAR looked like back then, because what it is today is quite different. We'll also talk about that. But yeah, bring me back in the early 80s when you joined NGA and some of the work that you start doing.
Okay, so I'm going to tell you a story. So first of all, I didn't do SAR till halfway through my career, but you can't understand the SAR part until I answer your first question there. What happened when I got there in 1983? Well, to say that, I have to say what my education was like before that. So I want to talk about that for a minute. So I was lucky in this weird sense when I was a child to have very difficult upbringing. Bad poverty, lots of problems. And that gave me a perspective on education that the only way out of it was to take school seriously and work hard. Right. So people relax in senior year in high school. Senior year in high school, I took calculus, matrix algebra, and physics. I wasn't messing around. And because of my situation, to go to a real college was unthinkable. I didn't even apply to any colleges. I went to City College in New York City, and I commuted by bus to my school. I took it very seriously. And I started as a math major, but I like to say I didn't know then what I know now, and that mathematics is the language of nature. And if nature is beautiful, so is its language. I couldn't see that then. So I stopped and I started taking environmental science classes like everybody now was going to save the world, And then I became a geographer because I had a wanderlust and I wanted to learn about other cultures. So I had the kind of education we tell young people now not to do. That is, I was bouncing all over the place. And that helped me all through my career. I took classes in the humanities. If I could say the two greatest things I ever did in college, classical music and English literature and writing. And I had a breakthrough in how to write and express myself. And those are the classes I loved the most. Anyway, after that, I got a full scholarship. I was able to go to University of Hawaii, which was remarkable, leaving Washington Heights, where I grew up, to go to a place like Honolulu as a geographer. So I had nothing technical in that degree, but I learned how to think. I learned how to come up with an idea to do research, how to defend it, how to follow up, how to write a thesis. I learned some remote sensing. And I thought, man, I need to do something practical. So I took classes in mapping. And my teacher, he would love your podcast, Mind Behind Maps. He would love that idea. My professor was like an artist, and he taught us all graphics. So there I learned this, again, nothing technical, graphics, how to think and how to do research. And then I got dropped in the precursor to NGA in the geodesy department. So what were we doing there? We were using NRO spacecraft of the early mid 1980s, which were film-based satellites. So they launched these massive satellites the size of buses, like 60 feet long, with film in it, pods of film. It was really a wonderful thing. And they would take pictures over East Germany, the Soviet Union, and the film buckets would be ejected from the satellites. They send out a parachute, fall over the Pacific Ocean. An airplane would grab them, scoop them out of the sky, bring them down to the ground, develop the film, and then it would come to people like me. So it was my job. Our job was to make the metadata, the geometric metadata for those satellites accurate so that you could derive coordinates accurately. And this is the era before GPS, right? So to do photogrammetry with optical imagery, we collected images in stereo. You need to know how was the satellite moving when it took its picture and where was it pointing? And those are the things we would figure out, right? So that's what I was doing. It wasn't SAR. But here's the thing. It was like a science fiction story. We had a UNIVAC computer. Maxime is 1983, 1984. That computer mainframe, it had 64K of RAM. And it had all these printouts, and all these printouts would come out of the computer and tell us what to do. But nobody understood anything. I learned the mechanics of how to work it, but I didn't know what I was doing. And I would ask questions and I'd get obscure answers. I didn't understand it. It was as if an advanced civilization came, like on a Twilight Zone episode, and dropped this computer, which we all worshiped. And we were these ancient, like cave-dwelling people. And we would do what the computer told us. And nobody knew what was going on. And that's what was happening. After a few months, I lost my fear. And I have a basis, as we said, in mathematics and physics. And anybody with a level, up to that level can teach themselves, in my opinion, any hard science up to at least a level of competence. So I got a hold of Ed McHale. He's a professor, now professor emeritus, Purdue University, photogrammetry. I read his textbook. I read the photogrammetry textbook from Ohio State. I got a hold of McHale's textbook on least squares adjustment, how to solve massive systems of equations. I got a book on geodesy, and I read a textbook. So I taught myself all this stuff. And then I went back to that UNIVAC computer, and I started going through all those printouts, and I started figuring it all out. And my coworkers, did they think, oh, what a nerd? No, they were encouraging me. It was like we were walking through a tunnel, and I had a torch, and we're all solving this mystery, getting the way out. And I became the guy who figured out the UNIVAC. I figured out all of this. And I realized my coworkers could understand this if it was presented to them in a comprehensive way that did not involve solving massive systems of equations and knowing how matrix algebra worked. And that's what I started to do. I started teaching my coworkers. Everybody signed up for the class. We had people on midnight shift. That's all they did. They worked midnight shift. They came and took my class. It was like vampires sitting in the back of the room. And it was the greatest honor I've ever received in my career to see those guys sitting back there, listening to me, explaining finally what they were doing and why, and what that freaking computer was telling them, right? And so I told my wife, don't bother me Wednesday night or Saturday morning. I'm going to write a manual. So on my Apple IIc computer, 9-pin dot matrix printer, I wrote an introduction to analytical triangulation, how it all works. And it was a manual, about 100 pages, 110 pages with illustrations. And it went to everybody. This was the era of Mylar overlays and an overhead projector, no PowerPoint or anything. That's how I would teach. And then I started adding stuff about the satellites, how they worked. And then it became a little bit digital, right? And we had PowerPoint, and I could make it colorful. I added prose and music from my background into my class. I learned other things about what the agency does, how you do stereo to make DEMS and other things. And I added geodesy, and I started to teach it. Essentials of Geomatics, I called it. And I started to get invited to teach in other places. All around the US, I started to teach. I got invited to go teach in the UK because they were our allies. Australia, Canada. And so that's what I was doing. managing some programs and doing that for optical imagery for the first half of my career. And I'm getting promoted and moving up slowly. And then one day, a guy in my office is managing a radar program. We're doing nothing with it. And he retired. I said, I'll take that. Now, I knew as much in that time as you learn about radar imaging in a college remote sensing class. That's it. That's all I knew. And what we were going to do with this, I had no idea, but I began to manage it and try to figure out what we could do and to start to learn it. And that's how I started with SAR. And the view of the agency at the time was very, very negative. People had tried to do some mapping in South America with aircraft stereo collection and it was a disaster. It didn't work. So when I took over this program, lots of skepticism from senior management. It's not going to work. It's not worth anything. I remember walking down the hall and seeing my ex-boss. And he said to me, "Hey, Tom, I heard you just made a career-killing move for taking over SAR." And he was teasing me, but that's how we started. But we had a few advantages. Here was an advantage. No history, right? Nobody done anything with this stuff before. So we didn't have to break stuff to do new things. In the government, there's so much bureaucracy and ingrained processes. It's very difficult for them to change things, even though they claim they're innovative. Very difficult to change established processes and systems. Well, we didn't have any of that. We're starting from scratch. We do anything we want. Plus, people were kind of ignoring us. Oh, it's that weirdo SAR stuff. So we felt like these renegades. People didn't like us. We're renegades. And here was another advantage. The place where SAR data was processed in this military intelligence complex, I can't give you details, but just let me say it was not in Washington, D.C. It was way outside the Beltway. So we were physically removed, and we got stuff done for that reason. So I have to say, too, when I went to the ground station and first met the director of the ground station, I walked into his office. He was an Air Force colonel at the time. I'll tell you his name because he's a hero. His name is Ted Cope, still around. Over his desk, a gigantic pirate flag. So we're instant brothers, you know? So you need to understand, that is how we felt, like pirates kicking doors in. People didn't like us. Ted's job at the time was he promoted innovation. He got us money and he protected us from the people who wanted to kill us, because there were people who wanted to do that. And we got a lot of wonderful things done. So that's how I started halfway through. And all of those things, sort of negative things, turned out to be advantages.
So what do you start doing with SAR? How do you get your hands? How do you start playing around with it back then? What are some of the moments where, even if there's some external skepticism, I'm sure a little bit of that kind of reflects on you at some point. Maybe you're like, okay, what did I get myself into? When do you start realizing, hang on, this is actually pretty cool. This is quite useful here.
Yeah, well, we always believed that. And I had some money too as a research project manager. I had funding. So what I always thought, and I still believe, if senior management can be very skeptical about things, go to the customer, right? And get the customer to fight your battles for you. So I went to Southcom. Hey, I want to do some work for you in South America, right? It's socked in with clouds. Not going to cost you any money. It may fail, but let's give it a shot. I want to try to do some mapping things for you in South America. And that's what our first project was. And we did some remarkable things. Unfortunately, I can't tell all the details of it, probably, even though it was almost 30 years ago, probably still a little bit classified. But we did remarkable things, mapping in areas in South America that had really never been mapped before. And I want to say, too, in NGA at the time, there were always mapping systems and intelligence systems, and they were different, very different. That's why they came up with the term geospatial intelligence, which tried to merge the two things. But at the time, you had geospatial systems and intelligence systems, and never the twain shall meet. We used an intelligence system to do mapping, and it was radical. My boss hated it. Her boss hated it, but the customers loved it. And here's what happened one time, just to show, so we have this prototype running and it's working and we're making stuff for Southcom. And I talked to people like this guy, Colonel McNichols. When I talked to him, his eyes would light up. I want to get stuff done. I needed to get some of that operationalized because it was all prototype. And I'm having Ted Cope's guys at the ground station do favors for me, and it's costing time and money. So I needed to get some of that operationalized, and I needed money, and I need to pass a couple of RFCs. These are called request for change, to change some government software. I went to go see my boss. She said, I need to go to the board this month to get approval so we can finally stop asking for favors. No, you can't go to the board. All right, I can wait one more month. You're not going to board this month. You're not going to board next month. You're never going to the board because we don't support your program. Well, who's we? It was her and her chain of command. It wasn't the customers. So what happened? I'm going to call her Olga. Olga went on vacation. And when Olga went on vacation, I got one of my senior customer people to schedule me for the board she told me I was never going to. So we actually went into the board with no money, no pre-approvals, and we got our RFCs passed. Because I walked in there with the head of Southcom, Colonel McNichols, and the director of operations of the whole agency who loved what we were doing, right? So I got the customer on our side, and that's how we got stuff done. Anyway, so get the customer to support you, and you can get things done.
I guess what I'm taking away from this is also that, like, reading your book, we'll get to that, and just learning about the technical aspects of a technology or just physics or math. You come at it and someone explains to you the physics, like maybe using examples, but there's all these stories behind it of how we actually got there. And these get a little bit lost sometimes. Something new comes up and there's skepticism around it. And there's a difference between having this technology, having, understanding the equations and the physics and the math behind it, and having people actually use it, because there's people in the process and it gets a little messy. I'm just reflecting on that.
Yes, and I don't know. I just think because we all felt that this was a vocation, I always thought there's two sets of people who are assigned projects and manage them, and people who dream them up and advocate for them. And that's what we were. And I want to say another advantage was the United States invented SAR in the 1950s. 1960s, it started getting used in aircraft. And then, of course, the military intelligence complex made classified systems. So they had to jump on the rest of the world, really. Yes, other people did things, but high-res SAR, we had to jump on them. And so we had brilliant people.
I'm not sure I understand what you mean by jumping on it.
The jump on them. We had it's the expression, we had an advantage in time. We started earlier than everybody else to jump on them.
As in other countries and governments and militaries.
Yes. So we had a, 15-year start, So all these people were working with me. Jack Jackowatz, who wrote one of the seminal textbooks on synthetic aperture radar way back in 1995. He ran a lab at Sandia National Labs. Ralph Fiedler, who still works at the Naval Research Lab. A guy named Bob Johnston in Goodyear, Arizona. Why Goodyear, Arizona? Because that's where SAR was invented. And you can imagine the Lockheed plant in that place had brilliant radar people. And so we had all those guys working together and good programmers, feeding operational people things they hadn't had before. Oh, you can do change detection. You can do coherent change detection, amplitude change detection. We can make you elevation models in places where you never had them before. And so while SAR is very strange and difficult to use, the users were generally enthusiastic and supportive of what we were doing.
So let's get back to SAR itself. You were hinting at the fact that there's also this element called phase. We talked about you can see through clouds. We've found a microwave that can see through clouds, so we start using that. It's a lot bigger than visible light, so there's this trick of having a synthetic aperture, which means that we can have a much bigger antenna, but synthetically with a small satellite that we can ship, so we can have our high resolution. But then there's this element of phase, and you mentioned it's because the antenna creates this coherent wave that's different from visible. Let's go there a little bit more. What does that entail? What are the consequences of that?
So if you imagine the sun or a light bulb in your office right now, it's emitting lots of different wavelengths of light, all offset from each other. A laser or a radar, all the waves are the same wavelength, and they're all in sync with each other. So that's the difference. And the remarkable thing, well, I like to say, the human species doesn't do anything more precisely than measure phase variations. You heard a few years ago of scientists detecting Einstein's gravity waves. That was done by measuring phase offsets with laser beams, right? Phase offsets. Now, SAR does the same thing. Now, the platform's moving and the wavelengths are longer, but it's the same thing. And so here's a remarkable fact. When you send a beam down to the ground, it reflects, goes in all directions, part of it comes back. The error in your measurement of the phase, was it at the peak, the trough, or somewhere in between? That's what I mean, is much, much less, not much less, much, much less than one wavelength. Holy shit. Even from 700 kilometers away. So SAR has a natural precision in measuring how phase changed from pulse to pulse. And that information is used to form a visible image that you look at. Now, we can talk about this a little bit later. One of the challenges of SAR is how do we make that phase information more easily ingestible and usable by people who are not scientists? Right now, we basically feed scientists that data. When I make you a SAR image, you see brightness pixels and you look at it and it's a little bit weird. All the phase information is thrown away and you don't get it. Scientists generally get that and they can do wonderful things. I saw your interview with Ian Woodhouse, and he talked about how he likes to do interferometry to measure elevations and very subtle surface changes. You need phase information to do that. So it allows you to do things like measure how the ground changed after an earthquake. One of the most remarkable SAR pictures I ever saw was from a low resolution SAR called, I think it was ERS1. The spatial resolution was about 20 meters or 25 meters, nothing impressive. But remember, phase resolution is much, much less than one wavelength. So it's not just spatial resolution. What is this phase resolution? So they had taken pictures over London over a series of years in the 90s. And they were building the Jubilee subway. What do they call it? Not the subway, the underground in London at the time. And so because they built this tunnel, the ground sunk a little bit and you could see it, centimeter level sinking of the ground from a spacecraft with 25-meter resolution, but much, much less than that in phase. You could see it sink. That's what phase can get you. Wow. And some other ones I've seen recently, the scale of this sinkage of the ground is in millimeters, a rate of millimeters per year. That's how precise SAR can be.
When I really grasped that concept that you can measure millimeter changes from not just something that's at 700 kilometers, but it's also going at 7 or 8 kilometers per second in
Yes.
velocity as well. So it's not just really high up, but it's going just stupidly fast.
Yes.
And we can measure a millimeter change like that. That's one of those moments that kind of made me pause and wait, what?
So actually, when I started, as we discussed mixing, SAR had this very negative, it's ugly, it isn't going to work. I started to call it the beautiful sensor. Half as a joke, but half serious because of all these other aspects of it. So I always called it you're not going to call my girlfriend ugly. She's beautiful.
This is an element I actually wanted to talk about. So let's go on that tangent. I've heard you also refer to some of the foundational equations that explain SAR as beautiful equations. And just reading some of your words, like there's something poetic sometimes about the way you write about physics, and I just wanted to linger on that a little bit more. And I know you touched on that earlier about some of the education you learned from English literature, but I wanted to ask you, why do you go out of your way to bring some of that poetry to something that's very clear cut and exact and precise?
I'm glad you asked that because some of our great science teachers have done that over the years. Carl Sagan used to do that. And I would say I first realized this when I was a little boy and I watched a French guy, Jacques Cousteau, talk about the ocean. He had a show called The Undersea World of Jacques Cousteau. And I would watch as a little boy with my mother and my sisters. And I couldn't believe somebody could talk about science the way that guy did. He had a poetic prose sensibility, and he instilled in me that view of science. And I've always had. I have a book full, a room full of science books with that point of view. So yes, and I studied these things in college, English. I've always read Irish poetry. And so I cheated a little bit. I watched your interview with Ian Woodhouse, and I know at the end you asked for a book. So I have a book for you, but I'm also going to give you a poem because both things matter, right? So yes, I wrote the book with that prose sensibility, and when I teach, I do that too.
Ian actually also mentioned, I'll link to his interview. We had a whole section at the end of our interview about art as well.
Yes.
And
Yes.
I don't know, there's maybe a theme with all the radar imaging people that I know that see a lot of value in the arts and the poetry.
Yeah,
I
I have a
appreciate
book
that a
here
lot.
called Art and Physics right up here. Science and music, etc. But I want to say an advantage I had in being self-taught. I'm almost complete. Of course, I listen to people give lectures on SAR, but I'm almost completely self-taught on SAR. And in fact, writing my book made me ensure I knew things. You don't know you know something until you can teach it to somebody else. So writing and teaching is a good way to learn. But because I come in from the side, when I saw some of these equations, for example, the equation for range resolution for SAR, it's simply the speed of light divided by 2 times the bandwidth of the signal. Now, what's the bandwidth? How much you can vary? We send a wave out like this. Well, we're going to vary the frequency of the wave. That's called a chirp. So it's only the speed of light divided 2 times how much I vary the frequency. That's it. It's the simplest equation you can imagine for this complex sensor, which tells you something remarkable. It's only a function of how much I vary the frequency. It has nothing to do with distance. I saw that was, oh my God, I moved the sensor further away and resolution doesn't degrade. No, it doesn't. That's astonishing. An electrical engineer would say, well, what did you expect? Of course. That's the difference. So it's a sense of wonder,
Yeah.
And so azimuth and range resolution for SAR are both independent of distance. In the early days of SAR imaging in the United States, that was a secret fact. You didn't want anybody to know that. It's like I'm making physics secret.
The fact that if you move the sensor, the spatial resolution doesn't change. That was secret.
Yes. I think like in the 1960s, that was the case.
Right.
Yes.
That's
right.
another one of those things that which is completely mind-blowing. So I'm going to repeat it just to make sure that people listening like internalize this. You can move the sensor. So you have this thing that takes these radar images and you move it away and the spatial resolution hasn't changed.
That's right.
And like we're talking, in your book, there's this example, and that really hammered it home for me of we've mapped the moon from Earth, and I think it was 70 centimeters. When I went to look at, like, there's some images of the moon that were taken from Earth. Like, that's 380,000 kilometers one way. That's nearly 1,000,000 kilometers, 500,000 kilometers round trip. And the spatial resolution doesn't change. Like, that's just bananas.
Yeah, I'm not familiar with imaging the moon, but it most certainly is true. Resolution for SAR is independent of distance. Now, SAR is not independent of distance because if you move away, the signal strength drops off dramatically, and that's a problem.
But this signal to noise ratio, then that's it's a different trade-off.
Yes.
So let's go back on that. I'm glad we talked about, and I really appreciate the sense of wonder that you bring to this. This is one of the things I wanted to talk, and one of the reasons I wanted to talk to you about. So we have this sensor that can measure these millimeter changes. Is at least the spatial resolution is independent of distance, but as you said, the signal degrades. So we send a pulse and we listen for a response, and the further away we're going to be, the less of that pulse we're going to be able to hear back. So what are the consequences of that?
If you ask me, what's the most astonishing thing? If you had to pick one thing, I would pick this. We just talked about something astonishing. I would have said earlier that resolution is independent of distance. That's astonishing. But the signal strength blows my mind. So let's imagine let's just consider one pulse. I'm going to send a pulse to the ground. Off it goes. It's strong. Let's say 2,000 watts. Big, young, strong pulse. Boom. Off it goes. Well, as that pulse travels through space, it kind of opens up. It's kind of funny. With optical, we think of photons. With SAR, we think of waves. It's really all the same stuff, but it's kind of some crazy wave particle duality. I don't know. So this wave opens up like a balloon. And it's like the skin of the balloon. As it opens up, gets bigger, the skin of the balloon gets thinner. And this happens with the square of the distance. So the further you are away, by the time that pulse hits the ground, it's really weak. And it hits something. It's going to reflect in multiple directions. And only a portion of that weakened thing is going to come back, and it opens up. So it's this big, wide open wave, and it's captured by only a little antenna, and only it's going to catch a part of that. So if the pulse is 2,000 watts when it leaves, at a typical distance for a spacecraft, how strong is the recorded echo? 10 to the negative 17 watts. 0.000000001 watt. Oh, God, that's crazy. When I first did that, I calculated that for RadarSat like 20 years ago. Oh, I made a mistake. Recoded it. Same answer. Well, I coded another form of the equation. Same answer. I spoke to an expert. What did he say? What did you expect? A brilliant radio astronomer. So that's how weak it is. So the signal has to be recorded and amplified. And that's why noise is a problem on SAR, because that recorded reflection is so weak. Any noise, that's a problem. So ask me, where does noise come from?
Let's go.
Let's go. Where does noise come from?
You don't even need me, Tom.
Here's my antenna. Here's the reflection. It hit the antenna. It's so weak. Noise is any microwave getting recorded that's not the signal. Well, where are other microwaves going to come from? And one source, which I talk about in the book, I love it, we all know about it. It's called the cosmic background microwave radiation left over from the Big Bang. So the Big Bang has microwaves. So imagine there are microwaves 13 billion years old hitting that antenna. And the antenna can't tell the difference between that and the signal. That's crazy. So I like to say some of those dots you see on a radar image are signals from the Big Bang. So when you see a beautiful optical image, ask the guy, you got any Big Bang photons on that? No, man. So what we do, we got Big Bang dots on our images. That's
That
crazy. And here's another wonderful thing about it. Think about it. Those microwaves are 13 billion years old. So an electromagnetic wave moving through free space is immortal. It never dies till it hit that antenna. But that's not the main source of noise. The fundamental principle of remote sensing is that all objects emit electromagnetic radiation as a function of their temperature. You're doing it right now in the thermal band. The sun does it in the visible band. Well, the receiver on the radar sensor also does it. It's not operating at absolute zero. And so it's emitting microwaves. So the receiver itself creates the microwaves which confuse it. I like to call this the poignant story of signals and noise. The signal's so weak, and the receiver does it to itself, and it can't stop it. Until someday we build them at absolute zero, it's not going to happen. So the receiver itself creates the microwaves that confuse it. And the great challenge of SAR is to separate signals from noise. That is the great challenge. And do a good job of it by making, in the end, an image that can have a million brightness values. The dynamic range of SAR is very deep.
How do you solve that?
Well, the brilliant radar engineers have figured out how to do this, how to amplify it, and those signals. And one thing that does help is this. I talked about one reflection from one scatterer. Well, it turns out that, remember, I'm pinging that guy multiple times.
Mm-hmm.
In a spotlight image, I might collect, let's say, for 10 seconds. If I do it at 3,000 times a second, that's 30,000 times I'm hitting it. And those all add up. So those weak signals add up 30,000 times. Plus, I get to use all of the reflections from the whole resolution cell, not just one little blade of grass. And that helps as well. So the situation is not quite as bad as I said. And you can separate signals from noise. That is why you do always have some noise on SAR images, whereas optical really doesn't have that problem. SAR, you see noise in areas that should be black, lakes, shadows. Yep. The challenge for the new little SARs, that is their challenge. Resolution really is not. They will achieve the maximum practical resolution of a SAR within a year and a half. But their challenge is signal to noise. They're not as good because they don't have these big antennas, right? They're not as good as the more established systems like TerraSAR X or Cosmos SkyMed.
You said, with big air quotes, you were retired. You serve as a consultant for a lot of new companies. Well, they've been around for a few years now, but these new space companies that are trying to drastically reduce the cost of SAR, sending these constellation. Like, what are you seeing as the future of SAR? Because, we've talked about some of the physics and how it works, but there's a lot of engineering as well of you need to build the practical thing that has a cost that, if you want it to be commercially viable, isn't too expensive. So where do you think we're heading?
One thing I want to correct is that I do some consulting, but only light consulting. When I left, I said, I want to write this book. Take me 2 years. Took me over 4 years to write the book, right? And I did some work for TerraSAR X, Cosmo, the RadarSat-2 people early on when I first left. That stopped. I did a little work for Capella for only a little while, and I've done work for ISI, but I don't take on new stuff. I don't want to work much. I teach a little bit, and I've done consulting for Capella, but that's kind of recently I said, but that's tailing off because I got hired by the US version of ISI, and they have ramped up their staff until they don't need me so much anymore. So that's good. I don't do too much for them right now. You know, again, in your interview with Ian, he talked about this. These little SARs, where's the money coming from? It's coming from mostly the U.S. military industrial complex, the NRO, NGA, where I used to work. And that's who's got the money, and that's who cares about really high resolution, which these guys are focusing on. So the focus right now for the little ones is to do really high resolution. And their customer, military intelligence, that's where money's coming from. Ukraine, in this horrible way, has helped them. Actually, it bothers me a little bit. You know, I have the advantage of being sort of an old guy. I'm half young and half old, and I look at what do I want to do? And I worked in that area, and I really don't want to work in that area anymore. You know, so that's part of the reason too. I'm kind of backing off from this. But I think what I'm going to promote the future, what ought to be, is to make the access to phase data easier. Right now, it's hard to get, and it takes skilled people and skilled tools to do stuff with it. We need to do the next step in SAR, which is stop bragging about clouds and darkness and get phase to people, to regular people, so they could do stuff with it without being a genius.
Do you? This is something that I've heard you mention before as well. How do we do that?
Before I answer that question, I want to say one other thing. When I started to learn SAR, remember I taught photogrammetry and geodesy because I saw this big disparity between what the textbooks had and what people were capable of learning, right? Well, in the SAR world, it's far worse. Think about it. It was difficult for optical geodesy and photogrammetry now, but for SAR, it's microwaves. It's not brightness pixels, it's not visible pixels. The geometry is completely different. Layover's different. You have foreshortening, it's all different. You've got phase, doesn't exist for optical. And the equations in the mathematics are even more advanced than they were for. So it's worse, far worse. So that's why I decided to try to teach this and write the book. So how do we make phase more available? And here's another problem. The language was developed by electrical engineers, right? And it's infused into the SAR world. And that language is intimidating and scary. For example, how do you get phase data? You order a complex image. Now, so let's say I'm a new person. I'm going to ask myself some questions. Oh, I would like to get phase data. Yeah, okay, we've got it. It's in this complex image. Well, what's a complex image? Oh, that's an image in which the SAR pixels have in phase and quadrature dimensions. What's that? Oh, one's the real value and one's the imaginary value of the pixel. I'm like, what are you talking about? That's what we've done.
Yeah.
Oh my God. You know what? So we got, here is the real number system. 1, 0, 3, 5, 6, fractions, negative numbers. What are imaginary numbers? Well, that's a number in which you can have a square root of a negative number, like -1. And so they were weird and they called them imaginary numbers. Well, that term has scared the crap out of people for over 200 years. In fact, the genius mathematician, Carl Friedrich Gauss, he was active in the early 1800s. He hated the term. He said, it is shrouded in mystery and darkness. You've chosen a term which is scaring the crap out of people. So we do that to mathematicians. He wanted them to call lateral numbers because the imaginary, his real number system, it's lateral. Oh, that's not so scary. But we have used a term from mathematics to regular SAR users, image analysts, which they don't know and which is very intimidating. Real and imaginary. What is that? Complex. Well, because we use a complex number. So I'm going to just change the language. I'm going to call it the natural SAR image. Now, that's not scary. Well, I can produce the natural SAR image with brightness pixels like you used to and phase pixels, right? Brightness and phase. And I could explain phase to you pretty easy. Well, what's phase? Was it at the peak, trough, somewhere in between? So I'm going to give you an image with two bands, brightness like you're used to and phase, which you're not used to, but it's going to be sitting in there just like a multispectral image has bands. Just have two of them. And I'm going to give it to you in GeoTIFF. Okay. So we could do that. I give you a natural SAR image with amplitude and phase in GeoTIFF, which whatever tool you're using to look at your image now will be able to ingest that. No change to it. So right away, I've taken intimidation away, and not only have taken it away, have made it more appealing. If I gave you a choice, I'm going to give you the natural SAR image or something with two bands or an inadequate one with only one band. Which one do you want? You want the natural SAR image. But for 60 years, we've been calling them complex images. And in phase and quadrature, real and imaginary. And you need to be a scientist with a special tool to mess with it.
This is back to what we were talking about earlier. It's, there's the technical engineering aspect. And what I'm hearing you're proposing is a language change mostly. And then, simplifying the axis. But at the core, it's the words that we use. It's not the equation. It's not changing the equation or doing a different engineering trade-off. It's the language that we use. And this is, I just find that fascinating that it really does matter, like the words that we use.
I was so thrilled to realize that Gauss hated the term because I hate the term.
Yeah, that's some validation there.
It is a language, and there's other language problems in how we say what an image is. I would use the term natural SAR image. Now, the natural pixel layout for SAR, if I'm flying that way, that's the azimuth direction. I image this way, that's the range direction. So the natural pixel layout is range azimuth for SAR. So the natural SAR image is in range azimuth. Or I could give you just the amplitude values in range azimuth. Or I could mess with them and put them on a map projection with just one height, an ellipsoid height, or mess with it more and give you an orthophoto. Do you see? So I've gone from here, the raw data, natural SAR image. Well, the raw data is the phase data. That truly is for scientists. But an image, the natural SAR image, amplitude and phase, range azimuth, amplitude image, every step away is further from the source data and less capable. What we often give people are these map projection images, and the language we use for them is confusing, and I don't like that language either. And by the way, I used to make fun of RadarSat. Beautiful, beautiful sensor, RadarSat 2. 23 beam modes, right? So an engineer would love it. Oh, we've got all these different beam modes because it's electronic and it's very flexible. But go ahead and order one of those images. You have to know what all of those 23 things mean. SGX, FXX, WA, it's horrible. And that's just for RadarSat. And now you got to learn the other ones. And so we have these problems of what the image names mean, whereas they could be simple. Natural SAR image, amplitude image, range azimuth, map projection image, ellipsoid. And everybody uses the same term, and you know exactly what it is. So the language we've infused in here is confusing and misleading.
I want to get to the book, and we've talked a lot about the contents are a lot of what we talked about. You've already mentioned wanting to teach and like wanting to share to others, and it seems like there's this deep core envy to make this more accessible. But writing a book is a really big endeavor. You said you thought it was going to take 2, it took 4. So what made you want to write this book?
Just as I wrote that manual, was it? I hate to say it, almost 40 years ago for photogrammetry and geodesy. I knew this was needed for SAR. I needed the book when I was young learning this. And there's nothing available. There's tutorial material, of course. And then there are the textbooks. And as valuable as they are for electrical engineers, they're unreadable for typical analysts, right? And the disparity, as I said, for SAR is worse than it is for optical. So this book was needed. I thought, oh, should I have it published, formally published? Well, I'm not a professor linked to a university, so I don't believe I have the stature to do that. And they would ask you, how many are you going to sell? I have no idea, So I did it on Amazon, self-published, and that's been really useful. But I knew one of the questions a publisher will ask you is, how many other books are there like this? You're going to have to compete against. The answer is 0. There aren't any. For SAR, this is it. There are no other books like this that a normal professional can read, be a little bit challenged, and learn it. There are the textbooks, but they're not going to read those textbooks. So that's why I wrote the book. And that's why it has so many illustrations in it. And conversational. It's not written in the style of a textbook.
What has been the response so far? I mean, I can tell you mine. I got so much value from it, but I'm curious to know what you heard back.
Well, just like I said, I was standing and teaching midnight shift vampires in the back of the class and how rewarding that was. Similar things have happened here. I've gotten responses from people in India, Saudi Arabia, Africa, Cameroon, Africa. Of course, the US and Europe too, but those, wow. Amazon makes it available worldwide. That's astonishing. And the feedback has been very nice, positive.
I want to ask you about the dedication letter at the beginning of your book. It's 2 pages at the very beginning. I think it's one of the first things in the book. And you write this letter to your dad, and you talk about being on a beach with him and him explaining to you waves on the ocean, and that the people in the boats are only going up and down and they're not moving. And, in fashion that we talked about, it's quite poetic about physics and engineering and understand all of those things. And I was quite surprised. It's quite lengthy and quite poetic. And so I just wanted to ask you about that.
Yeah, well, thanks for mentioning that. I wanted to give, first of all, dealing with a long-standing sorrow, of course, in that letter written to my father, right? But I also wanted to give the reader a little bit of a lesson that something simple, if you think about it carefully, isn't really simple at all, right? I often call it dwelling in the obvious. Something very simple, if you think about it and ask questions, you can go really deep. And of course, the nature of a wave is something like that. So I wanted to teach the user something about what we were going to talk about in this book, which is a book about waves. That's what it is. And give them an appreciation for it and let them know right away that this is something beautiful and deep. And how could I do that? I don't want to give them a lecture. right? So I wanted to do that without lecturing. And that's why I wrote that letter.
I appreciate that.
Yeah, thanks.
You also mentioned you've done some teaching. Is that different from, is that a part, because I know you've done a course, for example, for ISI. You could make an argument that that book is a form of teaching. But I wanted to ask you also about some of the teaching work you've done. And
Well, as I said, I used to travel around teaching what I call the essentials of geomatics, geodesy, photogrammetry, all of that. Um, and then I started to teach radar to the same group of people. But now that I'm on the outside, I do get invited to teach occasionally. I actually don't even advertise it on LinkedIn because I don't want to get asked too much. So I injured my back right before I left NGA, real bad. I was in torture level pain on the floor for 5 weeks. And that made me philosophical about life, the passage of time, what I wanted to do with life. And I had surgery and they fixed it. So a week later, I went and I left. I retired because I wanted to do new things while I was still relatively young and healthy. Write this book, teach, do some light consulting. But I do lots of other stuff that has nothing to do with this. Do some traveling. I lived in Honolulu for a while as a young man. I was on the beach one time, and here come all these outrigger canoes, all the way from Molokai across 40 miles of ocean to Honolulu. Well, somebody came here from Oahu recently with 4 outrigger canoes. So I'm in this Hawaiian outrigger canoe club, and it takes a lot of my time. We even paddle in the winter here. We have a canal, we have a bay, we have the ocean, and I take that really seriously. I'm the secretary of the club. I travel, I have grandchildren. So I only do this professional stuff a little bit. I was recently in India teaching SAR, and it was wonderful. And those guys really appreciated it. And so I teach once in a while, but I don't want to have to travel halfway across the world like that too often. That's a long trip. Um, so anyway, my life is a mix of teaching occasionally, less consulting than I used to for the reasons that we just talked about earlier, and all these other things that I do.
actually, one of the things I wanted to ask as well is I heard that you had to get NGA's approval when you wrote that book.
Yes, they actually were really good about it. Now, there's a couple of weirdo. Well, of course, I can't talk about anything classified. There's nothing classified in that book. And in fact, my references were trigonometry books, geometry books. There's nothing in there that's not known. There's nothing advanced. And I wasn't revealing anything, but certainly I had a clearance, a top secret clearance. I can't do things without getting approval, but it went through very smoothly. And I was happy about that. So, no problem.
Yeah, but it must be still, I don't know, it must be something about you're not just writing any book, you're writing a book that you need NGA's clearance on. Were you ever worried that, some of your work was just going to go out the window?
Yeah. So, anyway, it turned out not to be. Well, one thing I did with that was, hey, I talked to the publication people. Why don't you get these 2 guys to look at it? Because I knew these 2 guys. And I mean, they would never do it just because of my friend, but I just made sure reasonable people were going to be the ones reviewing the book. And that's who they gave it to. So they were reasonable. And in fact, they were very good because they gave me comments and I made little changes based on their edits.
One thing you mentioned earlier was, and this is moving a little bit away from SAR, is your education was what we tell people not to do anymore.
That's
you said
right.
you were jumping around. And so, you're on the other end now. You're doing some of the teaching we just talked about. Your book is, one of the ones, I'm sure there are people out there that, just like you were doing back then when you picked up some of those textbooks, there are people that are probably picking yours up and studying without asking anybody and then just picking it up. What do you think is, it seemed like the way you phrased that, it's what we tell people not to do I felt like the way you were saying that's not really what you think.
It isn't. What we tell people to do quite reasonably is focus on something specific that's going to get you a career, right? That's what we do, especially in the United States. I don't know what it's like in Europe, but university education in the United States has become unbelievably expensive. It's really bad. And so you don't want to go do that with some vague idea. You want to do that and come out with, I'm going to get a job because I did this. But that's really not the basis of university education. I went in there and it opened my mind to all these different things. And, I think the poem, the road less traveled, I took the road less traveled by, and that has made all the difference. Um, I went to City University, so it cost me very little money. We also have a view in the United States. I don't know. I hope you don't have it in Europe, that you have to go to prestigious school to get stature. A lot of people do that now. Well, whereas anybody who works hard from any decent school can draw out of that all the information they need. You don't have to go to prestigious school, but we have that view in the United States. Because you went to some elite school, you have more stature than somebody else. That's a corrupt idea.
I think the road not taken, I think, is a reference that you use in your book actually at some point to talk about super resolution. And
I think yeah.
I want to talk a little bit about AI actually, and I'd love to have your thoughts on. So super resolution is one of them, but super resolution is trying to basically increase the resolution of an image. So we talked about, for example, a 20-meter image previously, and it's using algorithms that have been trained on higher resolution images to try to upscale an image to something that would be 10 meters or even 5 or more. So that's super resolution, and that's being talked about recently quite a lot with a lot of developments in machine learning. There's also a lot of developments at the moment that might help in interpreting some of the more complicated data. And some people have pushed forward some ideas of, that could really help increase the accessibility of not necessarily SAR data, but extracting information from it, which is what, arguably a lot of people care about. A lot of people don't care about the images. They care about, is that a tank in there? And was it there before? And I don't really care how you know.
Right.
So, this is a bit of a long-winded question, but I'm curious to know what you think about this whole field of AI and machine learning coming in SAR.
Yeah. So obviously, it's remarkable how much it advanced over the last just 5 years. We've seen Chat GPT and been astonished by it. I downloaded an app that lets you do drawings. I was thinking of using it for my teaching. It didn't work out, but I asked it, draw me a picture of a yellow vase with red roses in a medieval castle on a stone table. And it did it. It did 5 of them. 2 of them sucked. 3 of them were beautiful, So I was like, can I use it? But it didn't know electrons. When I tried to have it do electrons, it didn't work. So that's remarkable. And Chat GPT, you can almost not know you're talking to a machine, So all of that has to be pursued, and some of it's going to work in the near term. Like, for example, ships. SAR's really good at seeing big metal things, especially big metal things on a flat surface where that's going to give you a dark signal. So automated ship detection with AI and machine learning tools we'll be using it if we're not already. It's gonna work. But there's so much hype associated with it that I do use a poem in the book about it. See, I think we need for science, you have two engines: openness and skepticism. And you need fuel in both those engines or you're lost, right? If you have no skepticism, then you're going to believe everything and you can't navigate. So I think for AI and ML, we need more fuel in the skepticism engine. It's harder than people are saying. It's harder than what government managers say that they're doing when they speak at big conferences and everybody claps for them because they have to, because they're the ones with the contracts and the money. That's what happens. So it needs to be pursued, but it's harder. And I think what I say in the book, this is the epitaph of William Butler Yeats: cast a cold eye on some of those claims. He said, cast a cold eye on life, on death, horsemen pass by. So we need to be open, but we need to cast a cold eye on some of the AI and ML claims while we fund it and hope for the best.
I felt like this is a great segue into asking you about that book and that poem that you wanted to share.
I know he's going to ask me, is there a book? So my office is full of physics and science books. Which one should I pick? And is there anything that stands out? I actually have one that no one else is going to tell you. I want to show it to you. This is it. It's called Who is Fourier? Look, French. Fourier, c'est moi. There you go. And this is written, it's called A Mathematical Adventure. It's written by a Japanese language institute. They call themselves the Transnational College of Lex. It's this crazy Japanese language institute writing a book about an engineering topic. Why? Because they care about the nature of sound. And Fourier's great insight was a complex wave can be broken down into the sum of many simple waves. Sound is a wave, and you can model it as the sum of many simple waves. So these guys are writing an engineering book with cartoons and simplicity that ends up on the abyssal plains of the ocean. So I love these guys. It starts out so simple and it's lighthearted. They're making jokes. It's nothing but cartoons written by language people on a mathematical topic that ends up really deep, and it's beautiful. I wrote them a letter. Hey, thank you. I read your book. I use it to describe the geoid. What is the geoid? The geoid is the gravity field of the Earth, moving around and undulating. The gravity is not constant, so it undulates around this 3D surface of the Earth. Well, we need an equation for that. So the geoid is nothing but this undulating 3D wave. And we use Fourier. It's broken down into the sum of many simple waves, just like these people do it here. And they wrote me back, thank you, Professor Ager. I'm not a professor, but I'm their friends. Anyway, who is Fourier? They wrote another book on DNA. I have no idea why, and I have it. And the quantum. I'm going to read those books next. Poem, Fern Hill, by the Welsh poet Dylan Thomas, because it's so beautiful. I think it is the greatest collection of words ever jumbled together in the English language, Fern Hill. It's a universal theme because it's the theme of childhood and time and change. And if you're really brave, you read that poem out loud. Let the words tumble out of your mouth and savor them because they're beautiful.
I think those are great words to end on. Tom, thank you so much for sharing the excitement. I think that is so important and something I value a lot. So thank you very much for your time, for sharing the wonder with me and everybody listening, and writing the book as well. I've gotten a lot of value. I understood a lot from there. I really recommend. I'll have a link to that as well. And for everything you do.
Okay, Maxime, thank you for doing these. Merci beaucoup. Au revoir. Okay.
I
Take
can't
care.
top that. Hey, thank you so much for listening to this conversation. I wanted to take a moment to thank the sponsor of this video, but also all the people who financially support me on Patreon. If everything goes well, these conversations should feel and sound seamless and effortless, but there's a lot of work that goes behind the scenes. I try to research and prepare these as much as I can to know who these people are and what makes them interesting and what would lead to a good conversation. I'm incredibly thankful to all the people who support my work on Patreon, meaning I can do a little bit more of it. This podcast started out as a way to learn more about the people in this industry, but I've also started making educational content on another YouTube channel that I'll put a link to in the show notes. And I want to make more content explaining how satellite images and maps work to a broader audience, as well as continuing to research the guests for these podcast episodes. So, if you value the work that I do, I'd like to ask you to please consider supporting my work on Patreon. There's also some behind the scenes of how this podcast is done and some of the work that I'm doing for these educational videos if you want to learn more about how I do all of this. Either way, thank you so much for all of your attention and your time. I really appreciate it, and I hope you get value from these conversations. Thanks.